Hey guys, my name is IBM and I welcome you to the next episode of Capacitance. Do not forget to subscribe, share the videos, you can download them, just learn with me. Like, write a comment wherever you find any challenge, I can always try to highlight that. Don't forget to watch the solved past paper questions for this unit of capacitance. Okay, so let's go. Remember, this is the Cambridge International Education and this is Physics 9702. So I think this is going to be capacitance C and this is going to be lesson 2. In lesson 1, just to remind ourselves, we introduced capacitance C and we say the capacitance C of a conductor was the ratio of the charge to the potential on the conductor. And we say that why the capacitance C could not apply to insulators. We explained why capacitance does not apply to insulators. We did several examples using the formula just capacitance equals to Q over V. Then in lesson 2, we want to dig deep into capacitance by looking at what we call the parallel plate capacitors, or we look at the capacitors themselves. So to begin with, in lesson 2, we are going to start by concentrating on the parallel plate capacitors, and we should look at the combination of capacitors, that is capacitors combined in series, capacitors in parallel, and so on and so forth. So most of the electronic devices such as radios, computers, and MP3 make use of components called capacitors. When you open any of the electronic device at your home, even the charger, whatever, it is going to have a capacitor in it. Reason being, later on when we study alternating current, we shall see that capacitors are used in rectification, that is converting alternating current to direct current. And because what is supplied or what is generated by electrical generators is basically alternating current, yet electronic devices at home use direct current, we always want to convert alternating current to direct current. That's why you'll find capacitors in almost every component that you see at home. But we shall not talk about the most complex capacitors, we shall refer to the simplest. The simplest capacitor in electric circuits consists of two metal plates with an air gap between them which act as an insulator. I know in most of the electronic devices you see at home, the capacitors are cylindrical like the ones you find in the laboratory. But the simplest capacitor is the one we want to discuss in this unit, which is the parallel plate capacitor, which is made up of just two plates placed side by side, and mostly in between them an insulator is placed. It could be air, it could be a rubber material, it could be a wooden material, what we normally call a dielectric. This curriculum stop prevents me from talking about a dielectric material or an insulating material between the capacitor plates. It just wants me to give the basics of the parallel plate capacitor. So we shall always represent the parallel plate capacitor by just drawing two parallel plates, such as this plate and this plate here. So the two parallel plates, one plate is going to be connected to say the positive terminal of a battery, the other plate is going to be connected to the negative terminal of the battery, which means the upper plate which is connected to the positive terminal will be entirely positively charged, and the bottom plate which is connected to the negative terminal will actually be negatively charged. So when a capacitor, when a capacitor is, when the capacitor plates are connected to the battery, as shown in the figure here, the battery is going to transfer excess electrons from the upper plate, which is positive, to the bottom plate, which is actually negative. So it is transferring electrons from the plate connected to the positive terminal of the battery to the plate connected to the negative terminal until the voltage or the potential difference between the two plates is the same as the potential is the same as the voltage supply, or is the same as the potential of the battery. For instance, if the battery is 20 volts, so the electrons will be repelled from the top plate to the bottom plate until the potential difference between the two plates is still is 20 volts. And when that happens, no more electrons can be repelled from the upper plate to the bottom plate. So it implies that the capacitor plates we are talking about here actually store equal but opposite charges. That's why in the previous lesson I mentioned that we shall always say that the capacitor does not store charge. But of course later on we shall see that the capacitor stores energy. So what is happening is that positive as we connect the upper plate to the positive terminal and the bottom plate to the negative terminal. So essentially what we can believe is that the negative charges in the upper plate are repelled to the bottom plate, so that we have more negative charges on the bottom plate and more positive charges on the upper plate, where there will be therefore a potential difference between the two plates. The potential difference continues increasing until the potential difference between the two plates is the same as the voltage supply, and at that point the capacitor stops charging. So uh, when the plates are connected to the battery transfers electrons from the plate connected to the positive terminal of the battery to the plate connected to the negative terminal until the voltage produced by the charge build up is equal to the battery voltage. So the PD between the two plates is going to be equal to the battery voltage with the time, and when that happens, it means a strong force of repulsion from the bottom plate onto the electrons, that no more electron can leave the upper plate to reach the bottom plate. So the electrostatic force is now strong enough to prevent electrons from leaving the upper plate to the bottom plate. And at that point, we say that the capacitor has been fully charged. So how do we define a capacitance of a parallel plate capacitor? Earlier on, we defined the capacitance of a conductor as the ratio of the charge to the potential on the conductor. But this time, we are being specific and we are concentrating on the parallel plate capacitors. So remember, the capacitor does not store a charge because total charge is zero. Because if I have 5 positively charged carriers on the top, when the capacitor has stopped charging, I have 5 negatively charged particles on the bottom. Therefore, the total charge is going to be zero. So can I say that there is no capacitance of the capacitor, because capacitance of a conductor was charge over V, because we are seeing total charge is zero? Not at all. To define the capacitor of a capacitance, then we shall concentrate on the charge on just one capacitor plate. So we are going to concentrate on the charge on one capacitor plate and the potential difference between the two parallel plates. So that will help us to define what we mean by capacitance of a parallel plate capacitor. So in defining capacitance of a parallel plate capacitor, it is different from defining just capacitance of a conductor. And we shall define the capacitance of a parallel plate capacitor as the ratio of the charge stored on one of the capacitor plates to the potential difference between the two plates. The ratio of the charge on one of the capacitor plates to the potential difference between the two plates, or the ratio or the charge stored on one of the capacitor plates per unit. When I say per unit, that is a ratio. Charge on one capacitor plate divided by potential difference between the two plates. That's what we call the capacitance of a parallel plate capacitor. So a capacitor will therefore look like this: that if the upper plate has a positively charged particle or has a positive charge Q, and the bottom plate has a negative charge negative Q, Of course, we know that the total charge is 0. So in defining the capacitance of a parallel plate capacitor, I said we shall define this as the charge on one of the capacitor plates, that is the magnitude of charge of one of the capacitor plates, over the potential difference V between the two plates. Now, remember I said when we connect the upper plate to the positive terminal of the battery, for example, and the bottom plate to the negative terminal of the battery, then I say the negative charges are repelled from the upper plate to the bottom plate. But remember the bottom plate is already negative. So if an electron is to move towards the negative plate, it must be overcoming the repulsion from the negative plate. So the work done to overcome that repulsion later on will be defined as the energy stored in the capacitor plates. The work done to overcome the repulsion when the capacitor is charging is later on going to be called the energy stored by the capacitor. So in physics, paper 4, you will use this as the circuit symbol to represent a capacitor, where you draw two parallel lines, and some students may just draw this and think that is a capacitor. Of course, you must add connections on it to show that this is a capacitor. So many times we shall use this symbol as the symbol for a capacitor. We shall not consider cylindrical capacitors for now. You will consider cylindrical capacitors and other types of capacitors if you do electronics and instrumentation at higher levels. For now, the curriculum just dictates that I concentrate on only parallel plate capacitors. A few things we need to note further. Number one, I want you to note that there are equal but opposite charges on the two plates. That one I've already mentioned. A capacitor or the capacitor plates will stop charging if the total positive charge on the upper plate is the same as total positive charge on the total negative charge on the bottom plate, which means the total charge is going to be 0. That's why I said, and I will always emphasize, the capacitor does not store charge, but it stores energy. One of the most common questions you expect in your exams is to explain why a capacitor stores energy but does not store charge. Many times it is 3 marks. Explain why the capacitor stores energy but does not store charge. Or explain why the capacitor does not store charge but it stores energy. I gave a simpler explanation. The charging process of a capacitor can be considered as separation of positive and negative charges. I said if we have a capacitor plate, or we have two capacitor plates where one is positive, connected to the positive terminal, and one is connected to the negative terminal. When we say the capacitor is charging, the negative electrons are repelled from the upper plate to the bottom plate, which is negative. So it's like the charging process involves separating charges. When charging stops, total positive charge on the upper plate is going to be equal to total negative charge on the bottom plate. So the charging process alone involves separating charges. At first, the energy required to separate the charge is small because the repulsion is small at first. But as we continue charging, more electrons accumulate on the bottom part. If more electrons accumulate on the bottom plate, for example, it means now repulsion increases. That means more and more energy is required to push an electron from the upper plate to the bottom plate because it's now experiencing even more repulsion. The bottom plate is becoming more negative, so it is causing more repulsion of further electrons to arrive to it. So at first, the energy required to separate the charge is small, but as charging continues, more and more work must be done to add more charge against the repulsion of what is already there. So the repulsion increases. That means more energy is required, more work is done. Thus, the potential of the plates increases. That means the potential difference increases, and the charging process becomes slower and slower. So with the time, the charging process becomes slower and slower because the repulsion is greater. It stops or it ceases altogether when the PD, that is the potential difference between the plates, is equal to the PD of the power supply or of the battery. So if the potential difference becomes equal to the PD equal to the potential of the power supply, then the charging process is bound to stop. So we say the capacitor is fully charged. And for this reason, therefore, the total charge is zero because the total positive charge on one of the plates equals the total negative charge on the other plate. So the total charge stored is zero. However, there has been work done in separating these charges. The work done in separating those charges is what is stored in the capacitor as energy. That's why we say a capacitor stores energy but does not store charge. I'll come back to this again to explain in more details or in simpler terms how a capacitor stores energy without storing charge. Okay, so let's first go to the combination of capacitors. So capacitors can be combined in series or in parallel, just like you did in AS and IGCSE. You looked at resistors combined in series and in parallel. Capacitors can also be combined in series or in parallel. So let's look at or let's explore a combination of capacitors, and we shall start with a combination of capacitors in series. So to fully understand this, or how capacitors are combined in series, I want us to first consider two capacitors whose capacitance is C1 and C2 connected in series as shown in this figure here. So here I've showed two capacitors. One is labeled C1, C standing for capacitance. Another is labeled C2, of course C is standing for capacitance. Let's say V is the power supply, which could be the battery. Let's C be the power supply, which could be the battery. So just like we had resistors in series, remember if you have resistors in series, let me just sketch resistors here in series connected to a power supply. Of course, we know that the current which flows into these resistors is the same. Just to remind you, current is equal to charge over T. So it's like current is directly proportional to Q. So since for capacitance, we are looking at charge over potential difference. So instead of current, we shall be talking about charge. So it's like the charge on each of these capacitor plates is going to be the same if they're in series. So number one, we have said charge is the same. If the capacitors are in series, the charge is the same. That means the charge on each of the capacitor plates is equivalent to the charge which would be on one of the plates of an equivalent capacitor. So if this is my equivalent capacity, means the combination of these two, the charge on each of the plates is still going to be Q because the charge is not going to add up. Then number two, if you go back to the resistance to the resistors, when the resistors are in series, the potential supply V is divided in the ratio of the resistances. So it also means for capacitors in series, the potential supply V is divided in the ratio of the capacitances. So part of it becomes V1 and part of it becomes V2. So now we have said the charge is the same for capacitors in series, but then the potential supply V is split into V1 and V2, which means V is going to be V1 plus V2. I want you to not forget that the capacitance C was given by Q over V. So if C is the combined capacitance, I prefer to use CT to mean C total or total capacitance. Then Q is the effective charge and V is the total PD. So it means I will have C1. C1 will be Q over V1 and C2 will be Q over V2. So if I make V1 and V2 the subject, then I will be able to arrive at an expression for the total capacitance of this capacitor. So I'm saying the charge is the same on each of the capacitor plates. That's number one. So the charge on each plate is the same and it is Q. So charge is the same, and I'm calling that Q. But then V is going to be V1 plus V2. And remember, if I make V the subject, V is going to be equal to Q over C total. That is, if I use C is equal to Q over V, so I make V the subject, so V is going to be Q over C total. Then it means V1 is going to be, because Q is the same, so it will be Q over C1, and V2 is going to be Q over C2. So I'm going to combine these expressions. So I'll say Q over C total, which is total capacitance. Where there is V1, I have Q over C1 plus, where there is V2, I have Q over C2. So doing the algebra, of course, Q cancels. So I have Q over C1 equaling to Q into 1 over C1, sorry, this was C total, 1 over C1 plus 1 over C2. So that means Q cancels out, so I remain with 1 over C total being equal to 1 over C1 plus 1 over C2. So what am I trying to arrive at here? If capacitors are connected in series, we treat them the same way we treated resistors in parallel. If capacitors are joined in series, we treat them the same way we treat resistors in parallel. If I try to make C total the subject here, or total capacitance, I want this to be the effective capacitance, C total. So C total or total capacitance, if you're a mathematician, product, this will be LCM with C1, C2, you cross multiply. Let me try to show this to students first, because many students, when I tell them just get product over sum, they're like, oh, where does it come from? So 1 over C total is going to be equal to LCM. LCM is going to be C1, C2. So C1, C2 divided by C1, you get C2 plus C1, C2 divided by C2, you get C1. So then I get the reciprocal. C total is going to be equal to the product C1, C2 divided by C1 plus C2. In general, if I have only two capacitors, I can find total capacitance from product over sum as long as these capacitors are in series. If I have two capacitors, I will find them from the product over the capacitances over the sum of the capacitances to get the effective capacitance. However, I want you to note, if I have many capacitors, then 1 over total capacitance will be equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus until you reach the number of capacitors that you want or that are given. But if there are only two, only and only two, it can be product over the sum as long as they are perfectly in series. So that is how we arrive at the expression for the capacitance of a capacitor in series. Okay, so I have said the capacitance have the same charge, but the PD is different, because I said the PD is divided in the ratio of the capacitances. And hence, of course, having derived this, I'll wrap this off because I have the same space to use. I think my students have now got this. You should be able to derive this equation by the way. So I have to wrap this so that my content can be seen clearly. I know some students don't listen, they just to see what is on the screen. So the total capacitance is given by that expression. We have already derived that. The total capacitance is got from the reciprocal of the capacitances. I said you should be able to derive that. That's why I have tried to derive it. You should be able to derive that. So the total capacitance is going to be equal to 1 over C total over 1 over C, which is equal to 1 over C1 plus 1 over C2. And I've showed you that if you have only two capacitors in a series, C total is the product C1, C2 over C1 plus C2 if you have capacitors in series. So if I have an n number of capacitors, hence if I have n capacitors connected in a series, then the combined capacitance is going to be given as 1 over C total equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus until you reach Cn. Now you might be asking yourself a question. Suppose I have identical capacitors. If you have only two capacitors that are identical, let's say C1 is equal to C2, which is equal to C. Of course, it simply means that total capacitance here will be C times C, which is C squared over 2C. So that would be C over 2. If you have capacitors in series, it's like total capacitance is smaller. If you have capacitors in series, it's like total capacitance is smaller. If each capacitor is C and there are two, it means the total capacitance becomes a half of C. It means if I have 3, total capacitance becomes a third of C. If I have 4, total capacitance becomes a quarter of 4. So it means if capacitors are in series and they are identical, total capacitance is always less than the capacitance of just one. If I have any capacitors which are identical, n capacitors which are identical, n capacitors which are identical, remember, if there are 2, I have C over 2. If there are 3, I have C over 3. If there are 4, I have C over 4. If there are any capacitors which are identical, then total capacitance is going to be C divided by N if they are identical. If you have any capacitors which are identical, let's say each has capacitance C and they are joined in a series, then it means total capacitance is just going to be C over N, because if there are 2, total capacitance is C over 2. If there are 3, it is C over 3. So it means if the number of capacitors increase in series, total capacitance becomes smaller and smaller. So for different capacitors in series, the combined capacitance is always less than the value of the smallest individual capacitance. Just like we saw in the resistors, if you had resistors in parallel, the total resistance was always less than the resistance of just one resistor. It was always less than the resistance of even the smallest resistor. So if I have one capacitor, say it is 2 microfarads, and I have another capacitor which is 0.5 microfarads, and they are arranged in series, I can predict that if I try to find total capacitance of these two capacitors, it will be less than 0.5. So for different capacitors in series, the combined capacitance is always less than the value of the smallest individual capacitance. The combined capacitance is always less than the value of the smallest individual capacitance. Okay, so I have given an explanation here that's worth noting. So you notice that the charge stored on both capacitors is the same if they're in series. Of course, I don't think you should be wondering how this comes about. Why is the charge stored on each capacitor plates the same? But of course, I know you do not wonder why the current through resistors in series is the same. But when a PD is applied, a charge Q arrives on the right-hand plate, which I call C1. This repels charge minus Q off the left-hand plate, leaving it with a positive charge. Then charge minus Q now arrives on the right-hand plate of C2, and then this in turn results in charge positive Q on the left-hand plate. So what I'm talking about is very simple. If I have two capacitors joined in a series, and let's say they are connected to a power supply. So you have two ways of thinking about this. If a negative charge arrives on the negative on one of these plates, because this is negative and this is positive, this will repel a negative charge. This will repel if, let's say, this is C1 and this is C2. So if a negative charge arrives here, it is going to repel. This repels a charge minus Q off this plate. It will repel a negative charge from here. And this charge, this will leave if a negative charge is lost from there, it means we have a positive charge there. And the negative charge which has been repelled from there is now arriving onto this plate here. If the negative charge arrives here, it will repel a negative charge from this one, creating a positive charge on this one, and the process continues and so on and so forth. On the other hand, we could think about this in the other way around, that if a positive charge, let me draw another diagram here. So this is positive, this is negative. So if a positive charge arrives here on this plate, it repels the negative charge from this plate. It repels the positive charge from this plate. So the positive charge repelled from here will arrive here. So this leaves a negative charge here. The positive charge which has arrived here will also repel a negative charge from this plate, will repel a positive charge from this plate, leaving a negative charge, and the process continues until the capacitors are fully charged. So that is essentially what is happening. That's why we say they have the same charge. The charge plates have the same magnitude of charge. That is what I'm talking about here. So alternatively, I've said a charge of positive Q induced on one plate of one of the capacitor, that is positive Q, will induce a negative charge minus Q on the other plate of the capacitor, which induces an opposite charge, positive Q, on the other capacitor, which induces another charge, an opposite charge, negative Q, on the neighboring capacitor, and the process continues until the capacitor is fully charged. So this will in turn induce a positive charge on one plate of the second capacitor and a negative charge on its other plate. Since initially the capacitors were uncharged and the charge is conserved, so finite total charge of the capacitor remains as before. Initially, before connecting the battery, the capacitors had no charge. That means by conservation of charge, the total charge should still remain zero on these capacitors. So when you connect a battery, a positive charge arriving on one plate induces an equal but opposite charge on the neighboring plate, which induces an equal but opposite charge on the neighboring plate, which induces an equal but opposite charge on the neighboring plate, so that in all cases, the total charge of the capacitor or total charge on the capacitor is still going to be zero. So the total charge remains zero. So those are capacitors in series. What happens to the capacitors if they are joined in parallel? So let's consider two capacitors C1 and C2 joined in parallel. If you recall, resistors combined in parallel. Let's say we have a resistor number 1 and resistor number 2, and these are joined in parallel. So what we remember about these resistors joined in parallel? We remember that the PD across each of these resistors was the same if they are joined in parallel, and it was the same as the power supply. The same thing happens to the capacitors. So it means the PD is the same. So the PD is going to be the same and is the same as the power supply if these capacitors are joined in parallel. So if the PD of the power supply is V, so it means the PD across each of these capacitors C1 and C2 is going to be the same as V. That's number one. Number 2, remember when current flows, it reaches a junction, and Kirchhoff's first law tells us that the sum of current into the junction is equal to the sum of currents out of the junction. So if this is I1 and this is I2, and the current coming was I, so remember I was equal to I1 plus I2. Because here we notice that, remember, I is equal to Q over T, and for capacitance we were talking about Q. So the charge leaving the battery is going to be Q, and the charge which leaves the battery is going to be Q, and when it reaches here, it splits into two parts. It splits into two parts. Let's say it splits into Q1 and maybe Q2. Just like the current, because at the junction, the current divides. Why is the current is dividing? It's because the charge is dividing. So it's like the charge is going to divide, but the PD across is going to remain the same. However, I want you to remember that the charge on each of the capacitor plates is actually going to be, it is still the same. The charge, that's why you see, the charge on each of the identical capacitor plates is the same. That's why you have positive Q1 here, negative Q1 here, which gives us a total of 0. Positive Q1 here, Q2 here, negative Q2 here, which gives us a total of 0, because initially the capacitors were not charged. So it means the combined charge is still Q. So it means the effective capacitor must have a charge of Q after combining these two capacitors, C1 and C2, to come up with 1. That one capacitor has a charge of Q. Just like if these two resistors were combined to form one resistor, the total current through it is still I. So that's why for the equivalent capacitor, I've said the charge on each of the capacitor plates is still Q and minus Q. Okay. So number 1, for capacitor C1, of course we know that V is equal to Q over C. Remember the PD was the same. But also remember that Q could also be written as C times V. Remember, the potential is the same. The potential difference is the same, but the charge is splitting at that junction. So we also know that Q, which is the effective total charge, is equal to Q1 plus Q2. The charge this side is Q1, the charge this side is Q2. Q1 and Q2 combine back to form the effective charge Q. Therefore, we shall have that for C1, the charge Q1 is going to be C1 times V, because the potential is the same. And for C2, the charge Q2 is going to be C2 times V, because the potential is the same. Hence, we are saying that substituting this equation, have C, I want to use C total. I want to say this is C total. C total times V is equal to Q1, which is C1 times V, plus Q2, which is C2 times V. Of course, there is a common factor of V, which means total capacitance for capacitors in series is simplest, in parallel is simply C1 plus C2. So for capacitors in series, total capacitance is the sum. For capacitors in parallel, total capacitance is the sum, which is actually the opposite of what we knew with our resistors. For resistors in parallel, you know that total resistance was the reciprocal. But for capacitors in parallel, total capacitance is actually the sum. I am saying you should be able to derive this. You should be able to tell the examiner that V is the same, the potential is the same. So you should be able to notice that the charge divides at each of the capacitor plates. That's why we have Q1 and Q2, but Q is the sum of the the charges which have divided. And if we substitute and remove the and V is a common factor, we come up with that expression there. So it means for capacitors in series, total capacitance is simply the sum of the capacitances of each of these individual capacitors. Hence, PD across each capacitor is the same. I've already mentioned that. And we have seen total capacitance is the sum of the capacitances of each of these capacitors. And for n capacitors, each of capacitance, for n capacitors, each of capacitance C, let's say, let me say each of capacitance C, for n capacitance C, for n capacitors, each of a capacitance in parallel, total capacitance is the sum of all the individual capacitances and is always higher than for a single capacitor. So if you have capacitors in parallel, you are increasing total capacitance. This concept is very important, especially when we reach alternating current at that part of rectification. The advantage of having capacitors in parallel is that we shall have a higher capacitance. A higher capacitance has an advantage during rectification, as we shall see when we talk about the time constant. So the individual capacitances, the total capacitance is the sum of the individual capacitances. Suppose we have n capacitors which are identical. If we have n capacitors which are identical, of course, in general, we could say total capacitance total is C1 plus C2 plus C3 plus C4 until we reach Cn. But if they are identical and each has capacitance C, for identical capacitors, total capacitance is just going to be the number of capacitors times C. Remember, if they were in series, it was C over N. If they're in parallel and they're identical, each having capacitance C, then it will be N times C. Because if you have 100 capacitors, you can't begin saying 2 plus 2 plus 2 plus 2 100 times. If they are identical and they are in parallel, then total capacitance is N times C. So that is how we combine capacitance or capacitors in parallel. So you must have now noticed that equations of capacitors in series is similar to the equation of resistors in parallel. And the equation for capacitors in parallel is similar to the equation of resistors in series. So it's like the opposite in both cases. So we can summarize this with a comparison type, a simple comparison table. In this table, we can now compare combination of capacitors with the combination of resistors, so that we are very careful and we are considerate, and we are able to identify the difference between these two. For example, for capacitors in series, the charge was the same. For resistors in series, the current was the same. For capacitors, I talked about charge. For resistors, you were talking about current mostly. For capacitors in series, total capacitance was got from the reciprocals. For resistors in series, total resistance was simply the sum. For capacitors in parallel, we say the PD is the same. For resistors in parallel, the PD is the same. So they have a similarity for charge. Of course, charge and current are somehow related because charge or current is equal to charge over T. Here, the PDs are treated the same way. For resistors, PD is the same. For capacitors, PD is the same. However, in parallel, total capacitance is the sum. Yet, for resistors, total resistance is the reciprocals. So you must be very careful to distinguish these two so that you don't fall victim of confusion. You should be able to manipulate these two so that you don't really mess them up. If you're dealing with the resistors that you did in AS, for series, you summed up the resistors. For parallel, you consider the reciprocals. For capacitors, it is now the opposite. Okay, so having understood that, let's see a few examples of a capacitance of a parallel plate capacitor. Let's see a few, if there are a few more examples. So, can define capacitance? Of course, this is an open question which asks you to define capacitance. You can define it the same way you define capacitance of a conductor as the ratio of the charge to the potential on the conductor, or you can define it in terms of the capacitance of a parallel plate capacitor as the ratio of charge on one of the capacitor plates to the potential difference between the two plates. The ratio of the charge on one of the capacitor plates to the potential difference between the two uh, to the potential difference across the plates, or the potential difference between the two plates, that is a capacitance. A sketch a graph to show how charge sketch a graph to show how charge on a capacitor varies as the PD across it increases. Of course, that one we have already seen it from the introduction part in lesson 1. The graph of charge against capacitance, a graph of charge against PD is a straight line. So we saw that this was a straight line. So it is charge against PD. That was a straight line through the origin. What does the gradient represent? If we try to find the gradient, you notice that from capacitance is equal to Q over V. We have plotted the Q against V, so Q is equal to C times V. If you compare this with the Y equals to MX plus C, the graph is going through the y-intercept, so there is no, it is going through the origin, so there is no y-intercept. So the gradient is going to be C. If I plot Q against V, so the gradient is going to be the capacitance. So this is equal to the capacitance. Then what does the area under the graph represent? The area under the graph. Of course, later on we shall see that the area, this area here under the graph, is going to represent the energy stored by the capacitor. Of course, the area here is going to be a half because it's a triangle. The area is going to be a half times Q times V, which is the same as a half times, where there is Q, I can put CV. So that becomes CV squared. And this is the energy stored. So later on, we shall see that the area under the graph is actually the energy stored by the capacitor. So we shall see that later on. Okay, that is example. I think that example is fine. We shall explore more on the area under the graph. Given a number of capacitors, each with a capacitance of 2.0 microfarads and a maximum safe working potential difference of 10 volts. What does this mean? It means the PD across one capacitor should not exceed 10 volts. That's what it means. That's what we mean by a maximum safe working potential of 10 volts. How would you construct capacitors of 1.0 microfarads capacitance suitable for use up to 20 volts? So this is the voltage supply. But remember, the PD across each should not exceed 10 volts. And you are given a number, so that means that there's no limit on the number. You have many capacitors. So how are we going to combine them to have total capacitance to be 1.0 microfarads? Now, the first thing to come into your mind, if you notice that total capacitance is less than the capacitance of just one capacitor, then the first thing to come into your mind is that these capacitors are most likely going to be in series, or there should be a series combination. So which combination gives us 1.0 microfarads? Let's check. So if capacitance is in parallel, in series, know that total capacitance is the product over the sum. So that is C over N if we have n capacitors. So total capacitance is 1.0. This is equal to 2.0 over N, which means N is going to be 2 capacitors. So we can have 2 capacitors in series. That will give us a total combination of 20 microfarads. Of 2 microfarads. Let's see if they're in series, what is the PD across each? So you don't just check. We have checked that we should have 2 capacitors in series. Then you can check if they're in series, is the PD across them less than, not exceeding 10, yet the voltage supply is 20. If yes, then you can go ahead and sketch that. So many times in an exam, you can sketch this by just doing this. Where this is 2.0 microfarads and this is 2.0 microfarads. But sometimes my students want to sketch everything, so they sketch the whole of this. Where they will put here 20 volts. Of course, the 20 is divided into 10 and 10, so it is not exceeding what? 10 volts across each of the capacitors, because the maximum safe working potential is 10 volts. So either when you sketch this, you must put this to show that they are terminals to the power supply, or you draw a complete circuit like this one here. Then part 2, we have capacitors giving a total capacitance of 2 microfarads, suitable for use up to 20 volts. Now, getting 2 microfarads, I don't think we can be able to use this formula here, because there is a combination between there is series and parallel. But remember, we have seen if we have 2 capacitors in series, their total is 1 microfarads. But remember, for capacitors in parallel, we sum up. So if imagine we have this one and we get another one, then we put the 2 in parallel, then we can have a total capacitance of 2.0 microfarads. You must have done the same in electricity, I remember. That is in IGCS and AS. So we have 2 capacitors in series. These give us a combination of 1 microfarads. And let's have another pair of capacitors again in series. So it means we now have a total of this is 1 microfarad and 1 microfarad, giving us 2 microfarads if they're in parallel. Because in parallel, we sum up the capacitances. So in every case, you must put the terminals to show that there is a power supply somewhere. Okay, or you can draw the battery at the bottom. So you have to check the PD across each capacitor not to be exceeding 10 volts, because the maximum safe working potential should be 10 volts. So if you have 2 capacitors in series, the PD across each is going to be 20 divided by 2, so it is 10, 10, 10, 10, and it means this is going to be correct. So that is going to be the correct combination. Okay, example number 4, if it exists. A 1000 microfarad capacitor in parallel with a 50 microfarad capacitor is connected to a 12 volt supply. Calculate total capacitance, the PD across each capacitor, the charge stored on one plate of each capacitor. So I want to minimize this space. I don't have enough space. So we have to find total capacitance. They are in parallel. We have 100 microfarads in parallel with 50 microfarads. For capacitors in parallel, we just sum up. So total is going to be 100 plus 50, which is 150 microfarads. So that is correct. Then the PD across each plate. Because they are in parallel, the PD across each of them is the same and is the same as the power supply. The PD across each of the plates is the same as the power supply. If I was to sketch this here, you have capacitor in parallel with another, then connected across a power supply. A power supply of 12 volts. So if the PD of the power supply is 12 volts, then it's the PD across each of the capacitors, so it is 12 volts. Then the charge stored on one plate of each capacitor. So for the one of 200 microfarads, remember charge is equal to C times V. Charge is C times V. The V is 12 volts. We have the capacitance of each. So for the first one, it is going to be 100 times 10 to the power of minus 6 times V, which is 12. For the second one, the charge is going to be equal to 50 times 10 to the power of minus 6, then times 12. I'll just check these answers using my calculator. For 100, I think it is this is correct, 1.2 times 10 to the power of minus 3. Then this one is going to be 50 is a half of that, which is 6.0 times 10 to the power of minus 4. I think these answers are correct. You can also check. A 100 microfarad capacitor in series with a 50 microfarad capacitor is connected to 12 volt supply. Calculate the combined capacitance. For series, since there are only two, for series, total capacitance is going to be the product over the sum. So that is 100 times 50 over 100 plus 50, because there are only two. If there were many, I would say 1 over this plus 1 over this equals to 1 over this, so that I later on get the reciprocal. So this is simply, let me check with my calculator, 100. I don't trust these answers because they were obtained by students, so I have to be very check. Maybe the student made a mistake. I could also make a mistake, of course. Divide by 150. So this is 33. I think this is correct. 33 microfarads. The PD across each capacitor. Because they're in series, the PD of 12 volts is divided. Now, when you become an expert, you'll be able to divide the PD in the ratio of the capacitances very easily, like an expert. But the PD across from V equals to Q over C, or from C equals to Q over V. V is C over Q. I mean, V is Q over C. Since we know the voltage supply to be 12 volts, and we know that the PD across 100 plus the PD across 50, it's going to give us the 12 volts. Note that the V is inversely proportional to the capacitance because they're in series, the charge is the same. So normally, some of my students use mathematical skills. I always don't like using mathematical skills, but they always use mathematical skills. They say, okay, because capacitance is inversely, because PD is inversely proportional to charge, they normally say, okay, I mean, PD is inversely proportional to capacitance when the charge is the same. They normally say that, okay, if 100 microfarads has charge If 100 microfarads has PdV and PD is inversely proportional to capacitance, then 50 is half of 100, then this will have PD of twice V. And then they would normally say 2V plus V should be equal to 12. Then, of course, knowing that V is the PD across 100 microfarads, so this will give them V as equal to 12 over 3, which is 4 volts. So they will say PD across 100 microfarads is 4 volts. Therefore, the PD across 50 volts, 50 microfarads is going to be 80 volts. That is simple mathematics. Another group of students will first find Q. Total charge Q is equal to total capacitance times the voltage supply. So total capacitance is 33. I want to use 100. That will be 5,000 divided by 150. I'm using this value here to be specific, to make the answer to be exact, instead of using 33, which was rounded off. So they will find total charge as total capacitance times the voltage supply. So that is total capacitance times voltage supply, which is 12. So they end up getting total charge as, let me see, times 12. So total charge is 400. Oh, yeah, the units have, let me check the units. Here, capacitance was in microfarads. So when I say 500 over 150, there is a micro here. So this is microfarad times volts. So this will be microcoulombs, I think. Okay, let me change this to be specific. I'm going to change this so that the units can easily come out. So this is microfarads, which is times 10 to the power of minus 6. To change this to coulombs. Then times V, which is 12. Okay, so 1 exponent minus 6. So this is giving me the charge as 4 times 10 to the power of minus 4 coulombs. So they normally students first get the total charge. Of course, because they're in series, the charge on each of the capacitor is the same and is the same as total charge. So having known the total charge, now it becomes easy to find the PD across each of the capacitor plates. I mean the PD across each capacitor. For example, the PD across 100 microfarads is going to be the charge, which is 4 times 10 to the power of minus 4 divided by the capacitance. I'm using V equals to Q over C. The capacitance, which is 100 times 10 to the power of minus 6. Of course, this gives you 4, I think, because 100 times 10 to the power of minus 6 is 10 to the power of minus 4. So this is 4 volts. Then the PD across 50 microfarads is the same as charge, which is 4 times 10 to the power of minus 4 divided by 50 times 10 to the power of minus 6, which is going to give us 8 volts. So you can use simpler mathematics, which my students use, or you can move the long way where you find the total charge, which is the charge on each of the capacitors, the capacitor plates, and then you just use V equals to Q over C. You will still be able to get the same answer. So you have these two answers as the PD across each of the capacitors. Then the charge stored on one plate of each capacitor, that one charge is total capacitance times the voltage supply, because they are in series. Then question number 6, I'm doing this because I don't have space to solve this. Not forget to watch the solved past paper questions in this unit to gain more confidence. Calculate the total capacitance of a 300 microfarad capacitor and a 600 microfarad capacitor connected in series. They are connected in series. We want total capacitance. For series, because they are only two, I will simply say total capacitance is the product 600 times 300 over the sum, which is 600 plus 300. Of course, this gives us 200. I want you to note that whenever capacitors are in series, total capacitance is always less than the smallest capacitor. Whenever capacitors are in series, total capacitance is less than the value of the smallest capacitor. Total capacitance is always smaller than the smallest capacitor there. So this is going to be 200 microfarads, which is even less than 300 microfarads. Okay. So here you have a self-check to check yourself. You can pause the video and you try to solve these questions. Number one, a 470 microfarad capacitor is connected to a 20-volt supply. Calculate the charge stored on one plate of the capacitor. I think that one is direct. The capacitance in A is now disconnected from a supply and connected to an uncharged 470 microfarad capacitor. Explain why the capacitors are in parallel rather than in series, and why total charge stored by the combination must be the same as the answer to A. Of course, the advantage of having capacitors in parallel is that total capacitance is going to be higher. For capacitors in parallel, total capacitance is going to be higher. So if we disconnect the first capacitor and connect it across a second identical capacitor, so they are going to automatically be in parallel. The advantage here is that the total capacitance is going to be higher. And why the total charge stored by the combination must be the same as the answer to A. Of course, number one, total capacitance here is going to be the combination of these two. It is actually going to be the sum. But then the question is, why is the charge going to be the same? By conservation of charge, the charge is going to be divided. The charge, remember, it is the first capacitor which has been charged. So it is going to share its charge with the next capacitor. So the charge is shared between the two capacitors, but total charge is going to remain the same. The charge which the first capacitor that we saw in part A obtained is going to be shared with the second capacitor, but the total charge is going to be the same by conservation of charge. So calculate the capacitance of the combination. Because they are they are now in parallel. We just sum up. Because they are two, I will just say n times 2 times 470. I'm using capacitance in parallel is equal to n times the capacitance of each. They are only two. So that, I think that gives us that answer. Then calculate the PD across each capacitor. The PD across each capacitor. Now we have total capacitance. Of course, the PD across each capacitor is going to be the same because they are now in parallel. But it is not going to be 20 volts this time. Since the capacitance has changed, and of course the charge remains the same, the total charge remains the same, then the PD is going to be the total charge divided by the new total capacitance. So the PDV is going to be the charge, which is 9.4 times 10 to the power of 3, that is in part A, divided by total capacitance, which is 940 times 10 to the power of -6. So this is, I think this gives us 9.4 power minus, so this is 10, of course. When you practice this, you'll be able to predict that when you have identical capacitors connected in parallel, if one was charged, initially this was charged 20 volts. So the 20 volts was now shared. I mean, the 20 volts was used to transfer charge from one capacitor plate to another capacitor. Therefore, the PD is going to be divided into two. So it's like energy is going to be, part of the energy is going to be wasted in transferring charge from one capacitor to another. In fact, half is going to be wasted. So that's why the PD is going to always be predicted to be half of the PD which one capacitor had. One capacitor alone was charged to a PD of 20 volts. Now it was brought to in parallel with another one. The total charge remained the same. The total capacitance was doubled, and if the total capacitance is doubled and the charge has remained the same, then the PD is going to be halved. So that's why we see that the PD is going to be 10 volts. Then calculate the charge stored on one plate of each capacitor. One plate of each capacitor. Now that I know the PD across the capacitor, each capacitor plate, I know the PD across each capacitor plate, and I know the total charge. I know the capacitance of each capacitor plate, then I will simply say Q is equal to Q is going to be equal to C times V. This time I'm not using total capacitance because I'm finding the charge on just one plate of each capacitor. Each capacitor has capacitance 470 times 10 to the power of minus 6, and the PD across the capacitor is 10 if they are now in parallel. So this gives me 470, I think this is 4.7 times 10 to the power of minus 3 coulombs, which is of course 4.7 millicoulombs. So you can also verify. I've tried to attempt for you part of that self-check, but you can still try to solve it. Then the continuation of self-check, you can pause the video and try to verify this. I'll not go through this. I'll just read through. Calculate the total capacitance of three capacitors, 200, 300, 600 connected in series. Remember, if they are more than two, you don't use product over sum. You have to do the reciprocals. But remember, at the end, you must get the reciprocal to get a correct answer. Many times, students will just say 1 over total capacitance is equal to 1 over this plus 1 over this. For example, they will say 1 over 200 plus 1 over 300 plus 1 over 600. Then they just put here the answer and they think that is the capacitance. So after getting this answer, you must again get the reciprocal. So LCM is lowest common multiple is I think 200. No, it is 600. 600 gives us 3 plus 2 plus 1. 3 plus 2 plus 1, which is 6 over 600. So I have again to get the reciprocal because this is 1 over C total. When you get the reciprocal, I think that is going to be 100. You have a number of identical capacitors, each of capacitance C. Determine the total capacitance C when two capacitors are in series. Of course, that one is very simple. N capacitors are in series, you just divide. Two capacitors are in parallel. We said you multiply 2 by the total capacitance. N capacitors are in parallel. You multiply N by C. That one is direct. Calculate the total capacitance of two 100 microfarad capacitors connected in parallel. That one is easy. You can try it out. Calculate total charge stored when charged to a PD of 20 volts. I think that one is a direct use of the formula. Self-check is still continued here. A capacitor of capacitance 50 microfarads is required. So you have 50 is required, but so the total should be 50, but only values available to you are you have 10, 20, 100. You may use more than one of each. How do you achieve the required value by connecting capacitors in parallel? Give at least two answers. Of course, a layman would see because I said you can use a capacitor more than one. You may use more than one of each value. So I can use 1 of 10 microfarads and 2 of 20 microfarads. So you have 20 plus because 20 plus 20 plus 10, these are capacitors in parallel. So you have two capacitors of 20 microfarads in parallel, but also in parallel with 10 microfarads. So you have something like this. So two of them is 20, 20, and one of them is 10. That is 50. That's one way. Another one would connect five of these in parallel. Another one would connect five of them in parallel. Another person would connect what is 100 times 100 divided by 100 plus 100. I think this gives us 50. That's what I think. 100 times 100 divided by 200. So another person would have two 100 microfarads in what? In series. Two 100 microfarads capacitors connected in series would give us 50. 100 microfarads, 100 microfarads, two 100 microfarad capacitor also giving us 50. Now in an exam, it is always good to draw a circuit which has the smallest number of capacitors. The conductance G of a resistor indicates how a resistor is at letting current, through a given voltage. It is the reciprocal of the resistance, so G is 1 over R. Write down equations for the combined conductance G total of two resistors whose conductances are G1 and G2 connected in series and in parallel. Of course, if G is the reciprocal of R, then it means 1 over G total should be 1 over G1. Of course, I'll leave out this question for conductance because it's not in this curriculum, but it is just going to get the sum of the reciprocals. Self-check is still continued. For each of the four circuits shown below, calculate total capacitance in microfarads. If each of the capacitor has capacitance 100 microfarads. Of course, if you are an expert, you know that starting with the one who's in parallel, okay, the one in series, I would say 1 over C total is equal to 1 over 100 plus 1 over 100 plus 1 over 100, which is 3 over 100. Then I get the reciprocal. C total is going to be 100 divided by 3. I think this is 33.3 recurring. Then in parallel, we just sum them up, 100 plus 100 plus 100. So here C total is going to be 300 because they are in parallel. Then here, they are two in parallel where we sum them up, 100 plus 100. This gives us 200 microfarads, but 200 is in series with this. So again, it will be product over sum because there are only two. So total capacitance here is going to be product 200 times 100 divided by 200 plus 100. So this gives us 20,000 divided by 300. So this gives us approximately 67 microfarads. Then here these two are in series. For series, we say product over sum. So these two will give us product over sum 100 times 100 over 100 plus 100, which is 50 microfarads. But the 50 is in parallel with C3. So 50 is in parallel with 100. So total will be 50 plus 100, which is 150 microfarads. I don't know whether those answers are all correct, but they should be. Yes, they should be correct. You can also try to check and work out and see if they are correct. I could have made a mistake, but I don't. It's less often, or it's less likely. Given a number of 100 microfarad capacitors, it is a number, so it is a large number. You can use as many as you can use as many 100 microfarad capacitors as possible. How might you connect networks to give the following values of capacitance? 400 microfarads. I think for 400, the easiest way is to have four of these in parallel, because in parallel we sum them up. We sum up the capacitance. I think that is the easiest way. Then 25 microfarads. When I see the capacitance is smaller than 100, it means most likely I should first think about series. Suppose I have four 100 microfarad capacitors in series, because I know two of them would give me 50, another two would give me 50, 50 in series with 50 in series with 50, again it gives me 50 divided by 2. Remember, for capacitors in series, total capacitance is equal to the capacitance of 1 divided by n. So if the total is to be 25, I would say 25 equals to C, which is 100. Sorry, 25 equals to C, which is 100 divided by n, which means n should be 4. So 4 capacitors in series. Then 250. 250 is actually uh, 250 is actually going to be, if I have two capacitors that are in series, they would give me 50. Two capacitors that are in series, they are going to give me 50. Then two capacitors in series that give me 50. Suppose now the 50 is added to one capacitor which is 100 and another capacitor which is 100. I think there I would have I will have 250. So the two in the series give me 50. Then the 50 should be connected in parallel with the other two capacitors which are also in parallel. So 2 in series with 2 in parallel. 2 in series with 2 in parallel. I think that gives us a total of 50. I mean a total of 250. Note that I just gave you one way, but there is more than one correct answer. Try to find, so as an assignment, try to find other ways of drawing, of writing, or of combining these capacitors so that you can have the total capacitance that has been given here. However, I said try to find answers that requires the minimum number of capacitors always. So it is always good to use the number of the arrangement which requires the minimum number of capacitors every time. You have three capacitors of capacitance: 100 picofarads, 200, 600 picofarads. Determine the maximum and minimum values of capacitance that you can make by connecting them together to form a network. Of course, maximum, they should be in parallel, because for maximum total capacitance, for parallel, total capacitance increases. So for maximum, they should be combined in parallel, which gives us the sum of these three, that is 900. Then for minimum, they should be combined in series. So for minimum, they should be combined in series. And you can try to check to find 1 over total capacitance is equal to 1 over 100 plus 1 over 200 plus 1 over 600. The LCM is 600, which gives us 6 plus 3 plus 1, which gives us 10 over 600. Then we get the reciprocal, 600 divided by 10, which would be 60 picofarads. So the minimum is going to be 60 picofarads. Okay, I think we have one more example. Actually, this was supposed to be a self-check. Then calculate the capacitance in microfarads of the network of capacitors shown here. So these two are in parallel. We just sum them up to get 20 microfarads. So in other words, we have 10 plus 20 plus 10. So 10, 10, 10, 20, 10. Now we have three capacitors in series. And in series, 1 over total capacitance is equal to 1 over 10 plus 1 over 20 plus 1 over 10. The LCM is 20, which gives us 2 plus 1 plus 2, which gives us 5 over 20. Then I get the reciprocal. Total capacitance is going to be 4.0 microfarads. I think that should be the end of lesson 2 of capacitance.
At 29 and I find myself wondering, what did happen to the last 10? I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we set the rewind. And I